In the last lecture, we investigated the wave propagation in some arbitrary direction with respect to the coordinate axis. Our main objective is to find out the wave propagation in a bound medium, and as we mentioned earlier, when you are having a bound medium, the freedom of choosing the coordinate axis is not really there, because choosing the coordinate axis in a particular direction may simplify the problem, at least algebraically. So normally whenever we are having the boundaries, the medium boundaries, we choose the coordinate axis so that it aligns along the boundaries, and then the wave propagates in an arbitrary direction with respect to the coordinate axis, because the wave is now incident on the boundary from some arbitrary angle. So in today's lecture, we investigate the propagation of plane wave at media interface. So what we are now saying is, instead of having an infinite medium, if I divide the medium into two semi-infinite media, so I have what is called a media interface. On the left side of this line, we are having a medium which is again infinite. On the right side, we are having medium which is again infinite, and the medium properties abruptly change at this location here, what is called the media interface. So on the left side of this, let us say we have medium 1, on the right side let us have medium 2, and let us assume that the conductivity for both the media is still 0, that means the media are still lossless, but the permeability and permittivity are different for these two media. So let us say the permeability for this medium is given by mu1, permittivity is given by epsilon 1, and for medium 2 the permeability is given by mu2 and the permittivity is given by epsilon 2. Let us say now we orient the coordinate system such that the media interface is in the xy plane. So let us say along this direction we have coordinate axis x, perpendicular to this we have axis z, and perpendicular to the plane of the paper, that is the arrow which is coming outwards normal to the plane of the paper, that is the y direction. We can again verify that we must have the right handed coordinate system. So if my fingers go from x to y, y is coming outwards from the paper, then my thumb must point in the direction of z. So this is the correct right handed coordinate system. Now let us say we have a wave which is incident on this dielectric interface at some arbitrary angle with respect to the coordinate axis. So let us say I have the wave which is incident at some arbitrary angle like that. So this is the direction of the wave. So essentially this is the wave vector for the wave which is incident on the dielectric interface. Now specifically we are asking questions like, when this uniform plane wave is incident on this dielectric interface, what will happen to this wave? Intuitively it appears that part of the energy will get transferred to the second medium, so that will again constitute some kind of a wave propagation. But also what is not obvious at this moment is that part of the energy will get reflected also from the interface. That is what essentially we will argue, that if the wave is incident on this interface, we essentially require two kinds of fields, one which will be existing in the second medium, and also the fields in the first medium also have to be modified to satisfy the boundary conditions. So essentially when the wave is incident on the dielectric interface, part of the energy will be transferred to second medium, but the part of the energy will come back to the first medium also, and that is what essentially we will investigate. When the energy comes back into the first medium or goes to the second medium, what happened to the plane wave nature, which direction the energy will be going? These are the questions essentially we have to ask for. Also we have to ask for what is the magnitude of the field which goes to second medium, how much power is going to get transferred to second medium. So the analysis of the plane wave at interface essentially includes finding out the direction in which the waves will be moving in the two media, how much power get transferred from one medium to another medium, how much power comes back from the interface to the first medium itself, what happens to the direction of the electric field, that means what happens to the polarization of the electromagnetic wave, and so on. So essentially in this lecture and the following lectures we will discuss these issues related to the propagation of a uniform plane wave across a media interface. And since we have taken a conductivity 0 for both these media, we can at the moment call these as the dielectric media. So this is the dielectric medium 1, this is the dielectric medium 2. So essentially we at the moment we are investigating propagation of a uniform plane wave at a dielectric media interface. On both sides you are having a media which are dielectrics. Now let us say this is making an angle with respect to this direction, that let us say this angle is given by some theta I. Now we define certain quantities here, that is if I say that xy plane is the media interface, that means in that plane suddenly the medium properties change. The medium is uniform in the xy direction, only suddenly it changes at this point along z direction, and without losing generality we can say this point is z equal to 0. So let us say the origin of this coordinate axis at the interface, and the wave vector is making an angle theta I with respect to this direction. Now this direction, z direction, is perpendicular to the media interface, so we call this as the normal to the media interface. So this line which is z axis is the normal to the dielectric media interface. So we are having now a wave travelling at an angle theta I with respect to the normal to the media interface. That is the problem essentially we are having. And now we want to ask, when this wave is incident at this angle, what will happen to this wave. So first of all let us represent this wave in the form that it has a phase function, it has an amplitude. So let us say, without losing generality, without specifically saying we are talking about electric field or magnetic field, we are having some field vector which is associated with this wave, but it has a definite phase function because it is travelling at an angle theta I with respect to coordinate axis. So in this case, if I write down as we discussed in the last lecture, the wave vector makes 3 angles, phi x, phi y and phi z with the 3 coordinate axis. So these 3 now angle we can write down in that terminology. So phi x is the angle which the wave vector makes with the x axis. So if I extend this like that, this angle will be theta I. So this angle which the wave vector makes with the x axis will be pi by 2 minus theta I. The angle which the wave vector makes with the y axis, which is perpendicular to the plane of the paper, that will be 90 degrees. So in this case phi y is pi by 2, and the angle which this makes with the z axis, that angle is phi z is theta I. Once I know these 3 angles which the wave vector makes with the 3 coordinate axis, then I can write down their direction cosines and I can write down the phase function. Since the medium properties for this one are mu 1 and epsilon 1, we have the phase constant for this medium beta, let us call it beta 1, that is equal to omega square root mu 1 epsilon 1, and in the second medium we have a phase constant beta 2, that is equal to omega square root mu 2 epsilon 2. So I know in both media the phase constant for a uniform plane wave, and we know the angle which the wave vector makes with the 3 coordinate axis. So let us say I have some field which is represented by for this wave, which is having a vector, and the phase function will be given as we saw last time as follows. So, let us say I have some field which is incident, and let me call that as some Fi, where F could represent the electric field or magnetic field, which is having a magnitude term. So, let us say it is F0I, which is a vector, and then we are having a phase function which is e to the power minus j. The wave is incident in medium 1, so its phase constant is beta 1. So, this is beta 1 into cos phi x into x plus cos phi y into y plus cos phi z into z. Now, since phi x is pi by 2 minus theta I, cos of phi x is sin of theta I, cos of phi y, which is cos of phi by 2, is 0, and cos of phi z is cos of theta I. So, from here we get cos of phi x will be cos of pi by 2 minus theta I, that is equal to sin of theta I. Cos of phi y is equal to cos of pi by 2, that is 0, and cos of phi z, that is cos of theta I, that will be cos of theta I. So, if I substitute this in the expression for the fields, in general the incident field, we call this wave is an incident wave, because that is what is incident on the dielectric media, and that is what this suffix denotes. This I essentially gives you the incident field. So, let us call this as incident wave. So, we have the field for the incident wave, which is this magnitude amplitude term e to the power minus j beta 1 x sin of theta I. This quantity is 0 because cos of phi y is 0, plus z cos of theta. So, the wave which is travelling at an angle theta I with respect to the normal to the interface can be represented by a field which is like this. So, if I look at some instant of time, if I look what is the variation of the field amplitude as a function of x and z and also y, the field variation we can obtain by taking a real part of this quantity. So, if I take the field amplitude at some instant of time, so amplitude or magnitude of the field that will be the real part of this quantity. So, real part of Fi and that will be F0I cosine of this angle, which is beta 1 times this quantity. Let us say I am interested in finding out what is the variation of the phase in the media interface. So, I am not worried about how the phase is varying in z direction. Yes, it has a phase constant which is beta 1 times cos theta I, but at the moment let us say we want to find out what is the phase variation which I am going to get at the interface when the wave is incident at this angle. So, I can take, since I have taken the origin z equal to 0 here, I can substitute z equal to 0 in this and I get the magnitude of the field in xy plane. So, that is z equal to 0. So, that will be your 0 I cosine of beta 1 x sin theta I. So, if I now look at the field variation, if I see in this plane, the xy plane, the field is having a variation which is cosine variation in the x direction, and it does not have any variation in the y direction. So, essentially if I plot at this field, so this is my media interface, and if I plot now the field amplitude will vary like that in the x direction, and it is constant in the y direction. So, essentially it has created some kind of a corrugated surface. If I want to visualize what this field variation is, this will be more like a corrugated surface in this plane where the corrugations are oriented in the y direction, because the direction perpendicular to the plane of the paper is the y direction. So, I got something like a asbestos sheets, which are these corrugated surfaces. So, one thing we note here is that if the wave is incident in this direction, the amplitude variation will appear like a corrugated surface in this xy plane on the interface, or it is equivalent to having a phase gradient in the x direction which is beta 1 sine of theta I. So, I can visualize this field either as the amplitude variation which is like this in the x direction and constant in y direction, or equivalently I can say that it is having a phase variation which is beta 1 x times sin theta I, or the gradient of the phase, spatial gradient, will be beta 1 into sine of theta I. So, this one has a phase gradient which is the phase change per unit length in the x direction, that will be equal to minus beta 1 into sin theta. If I make theta I 0, then the phase gradient will become 0. So, the phase will become constant, and that is what will be the case if the wave is moving perpendicular to this plane. So, if the wave was coming perpendicular like this, then this theta I will be 0, and then this will be constant phase plane. So, I will not have any phase gradient in this plane, and wave will be travelling normal to this. So, direction of the wave as it changes, it introduces a phase gradient on this plane. So, the creating a phase gradient and tilting the direction of the wave, they are equivalent. That means, if the wave direction is changed, I get a phase gradient. Equivalently, if I create a phase gradient, I will get a wave which will be oriented at some other direction, which will satisfy that phase gradient. So, from here, if the phase gradient is given to you, that phase gradient if I equate with this quantity minus beta 1 sine of theta I will get some quantity theta I, that is the effective direction at which the wave is travelling. So, now here what we did, we started from the wave direction and we said this is the phase gradient will be created, but now we can go reverse and say if the phase gradient was created by some mechanism, then equivalently the wave is travelling at an angle which will satisfy the phase gradient to be equal to this. Now, in this case the wave was travelling in this direction as we saw, which was making an angle theta I with respect to this. So, if I take a direction like that, this was the angle which was theta I. So, this wave which is moving at an angle theta I with respect to the normal has created this phase gradient. Alternatively, I can say if I had created this phase gradient, it would be equivalent to having a phase which is coming like this. Now, if I consider this dielectric interface, it will be immediately clear to you that even if the wave was incident from this direction exactly at the same angle, this angle same as theta I, it also creates exactly the same phase gradient, because they are making exactly the same angles with respect to the normal. So whether the wave is coming this way on the interface or the wave is coming this way from the interface, both are going to create identically same phase gradients. So if the wave which was traveling through the interface like this, then it will correspond to this phase gradient. If the wave was passing through the interface like this, it will create the wave gradient which is like this. Now this side we have medium 1, this side we have medium 2. So firstly, if I take this wave and take on this side, essentially the same phase gradient corresponds to a wave which travels away from the interface at a same angle, because this is the phase gradient which corresponds to this wave, which is same direction. So a wave which is approaching to the interface and wave which is going away from the interface at the same angle made with respect to normal create the same phase gradient, and that is a very important thing. Once we understand this, then we can now ask a question: when the wave was incident onto this dielectric interface, what would this wave do? So this wave, because of the continuity of the fields, would try to excite certain fields in this medium, second medium. Now in second medium, if I want to maintain the continuity of the electric and magnetic fields both, but once the electric and magnetic fields are induced into second medium, they see infinite medium ahead of it. That means again they constitute a wave phenomena, and since the medium seen ahead of them is the infinite medium, they again see a transverse electromagnetic behavior for the wave. So the ratio of the electric field and magnetic field again is decided by the medium parameter, and now the wave in the second medium, so the ratio of electric and magnetic field are decided by the characteristic impedance or the intrinsic impedance of second medium, whereas the electric field and magnetic field ratio was decided by the intrinsic impedance of medium 1 in this region. So if I say that the fields are continuous across the boundary, and on one side the ratio of E and H are satisfied by intrinsic impedance of this medium, on the other side the E and H are related through the intrinsic impedance of second medium, it is immediately clear to me that just by having the fields on the other side and the original field which are on this side, I cannot satisfy the boundary conditions for both electric and magnetic fields. So what that means is I have to induce certain fields in the first medium itself, or in other words, we have to modify the fields in the first medium so that the boundary conditions can be satisfied for both electric and magnetic fields at the interface. So essentially there will be some fields which will be induced in this medium, there will be some field which will be induced in this medium, and since the inducing phenomena is due to this phase variation, because this is the one which is created by the incident field, both these fields which are induced on two sides of the interface, they will have the same phase variation, because that is the origin. The field induced fields are because of this field which is incident and which is having this phase variation. So essentially what we note now, that the field which go into second medium, which field which get induced into first medium, they also should have a phase variation which is same as this phase variation, because they are caused because of this. And since this phase variation it is uniform in this direction, these fields also must constitute a phenomena for which the field is constant in this direction. And as I mentioned, since these fields are time varying fields, again they will constitute a wave phenomena. So the induced field in this medium will constitute a wave phenomena. Fields in this medium again would constitute a wave phenomena. And these fields will travel away from this boundary. These fields which are here will again go away from this boundary. So we will have two types of waves which will be going away from the interface, one this direction, and one will be the incident field here. So what we see, we have something which is going like that, there is another wave which goes like that in this, and all these three waves have the same phase variation. This is what is important thing to note. Now, for this wave, the wave vector lies in the plane which is plane of the paper, which is xz plane. So, if the amplitude is constant in this plane, if there is no phase gradient in this plane, then the wave normal lies in the plane which is the xz plane. So, if we define the plane of the paper as what is called the plane of incidence, which is the plane contains the wave vector and the normal, that is the plane which is the plane of the paper, we say this is plane of incidence. So, a wave vector for the incident wave lies in the plane of incidence, and this plane of incidence is perpendicular to the direction in which this amplitude is remaining constant, which is this direction, y direction. But the same is true for the two waves which are created, which are induced because of the dielectric medium interface. So, for this field also you are having a uniform variation in this. That means the wave vector corresponding to these two waves also must lie in this plane, which is the plane of incidence. So, what we conclude, make a very important conclusion, that the wave vector for the incident wave, for this wave, induced wave which is in second medium, and the wave vector which is going into first medium, they all three lie in the same plane, and that plane is the plane of incidence. As we mentioned, this wave, since it is going away from this interface, this will carry some energy. So, we will say part whatever energy came to the interface, part of the energy was reflected from this interface and part of the energy was transmitted to the interface. So, in general we see that when the wave is incident on a dielectric interface, there will be a reflected wave which will carry away some energy which was brought by the incident wave, and there will be what is called a transmitted wave which will take the energy to the second medium. So, we call this wave as the transmitted wave, and we call this as the reflected wave. Transmitted wave is also referred as a refracted wave, and this wave which brought the energy towards the dielectric interface is the incident wave. So, we have now got something important conclusions. When the uniform plane wave is incident on a dielectric interface at an angle, we induce two waves. One is called reflected wave which is going away from the interface in medium 1. We induce another wave which is called transmitted wave which is going away from the interface in medium 2. All these three waves have the same phase variation, which is minus beta 1 sin theta into x, this is the phase gradient, and all this wave vector for these three waves lie in the same plane, that is the plane of incidence. Now, if you recall, the light is a transverse electromagnetic wave, and in the high school we had studied the laws of reflection for light, and the first law of reflection was that the incident ray, the reflected ray and the refracted ray lie in the same plane, which is the plane of incidence. So, essentially that statement, the first law of reflection, comes from matching this phase condition on the interface, and that says that these three vectors which lie in the same plane. Now, the wave vector in optics is referred to as the direction of the ray. So, this is the ray in which the light is moving. However, when we go to general electromagnetics, we call that direction as the wave vector. So, we are now having a general statement, what is called the first law of reflection, that is the wave vectors for incident, reflected and transmitted wave lie in the same plane, the plane of incidence, and the plane of incidence is the plane which contains the wave vector and the normal to the interface. So, we got the first law of reflection established by this phase condition. Now one can ask this next thing is that when the waves are moving in this direction, in what direction the wave would be moving with respect to the normal. So since this angle is theta I and this medium is same, the phase gradient whatever I have, if I divide that quantity by beta 1 and take sine inverse of that, that would give me the direction of the wave propagation in that particular medium. So the direction at which the wave moves is, if I know the phase gradient, the first phase gradient whatever is created, if I divided that by the phase constant of that medium, then sine of the angle at which the wave travels, that is given by that quantity. So from here I can write here the phase gradient divided by the phase constant. So the angle which the wave makes with normal, let us say that angle is theta, that is nothing but sine inverse of the phase gradient divided by the phase constant. Sine inverse. So if somebody has given me the phase gradient, then I can take that phase gradient, divide by the phase constant in that medium, take a sine inverse of that quantity, and that essentially gives me the direction of the wave motion in that medium. So in this case, in medium 1, let us say this angle at which the reflected wave goes is denoted by theta r, angle of reflection, and let us say the wave which goes in this medium is given by theta t, we call as theta transmission angle. So we have a situation where the incident wave is at an angle theta I with respect to normal, the reflected wave is at an angle theta r with respect to normal, and the transmitted wave is at an angle theta t with respect to normal. So we are having now a situation which is one wave is like that, let us say this is my normal, this angle is theta I, something goes at some other angle, this is my reflected wave, let us say this angle is theta r, and at some other angle this thing goes, I call this as transmitted wave, so let us say this angle is theta t. So this is incident wave, this is reflected wave, and this is transmitted wave. And I am having a phase gradient on this surface, phase gradient which is minus beta 1 sine of theta. I will put a minus sign here. So what I can do is, if I see in medium 1, I can substitute this phase gradient value, and sine inverse of that quantity or sine of this angle will be equal to the minus of phase gradient divided by the phase constant. Now in this medium the phase constant is beta 1, in this medium the phase constant is beta 2. So sine of theta r should be minus of phase gradient divided by the phase constant. So from here I get sine of theta r, that is equal to minus times the phase gradient which is beta 1 sine theta I divided by phase constant which is beta 1. So this is minus times minus beta 1 sine theta I divided by the phase constant in the medium which is medium 1 which is beta 1. So this is equal to sine of theta. So this implies your theta r is equal to theta I. This is your second law of reflection, that the angle of incidence, angle of reflection are equal. So, whatever angle the wave is incident, at the same angle with respect to normal, the ray will be reflected, or the wave vectors will be making same angle with respect to the normal. This will be going toward the interface, this will be going away from the interface, but these two angles are equal. So, we see another important conclusion from matching of the phase angle, that these two angles are equal. Same thing we can do for the second medium, and that is, if I go to this in medium 1, which was for the reflected wave, if I go to medium 2, then the angle which this thing makes is theta t. So, sine of theta t should be equal to minus of phase gradient divided by the phase constant, but the phase constant in this medium is beta 2. So, we get from here sine of theta t, that is equal to minus beta 1 sine of theta I divided by beta 2, because we are in medium 2 now. So, from here essentially I get beta 1 sine of theta I, this term is equal to beta 2 sine of theta t. And we know beta 1 and beta 2 in medium, which is nothing but beta 1 is omega into square root mu 1 epsilon 1, beta 2 is omega square root mu 2 epsilon 2. So, if I substitute in this will be omega square root mu 1 epsilon 1 sine of theta I, that is equal to omega square root mu 2 epsilon 2 sine of theta t. The omega cancels. So, this relation is independent of what is the frequency of the wave, and that is square root of mu 1 epsilon 1 sine of theta I, that is equal to square root of mu 2 epsilon 2 sine of theta t. This relation is nothing but the Snell's law, which we have already studied in our high school. Of course, when we are studying the Snell's law there, we talked in terms of the refractive indices of the medium, and of course we dealt with only dielectric media. So, we did not have the permeability problem because the materials were not magnetic. So, we talked only in terms of the refractive indices of the medium, and we can see from here how do we get that special case that when the media are only dielectrics and the permeability of the medium is same on both sides, the relation essentially reduces to that relation in terms of refractive indices. But this is the important law which tells you the direction of the transmitted wave with respect to the direction of the incident wave for the given media parameter. So, this is, we can call it the generalized Snell's law. So, from here now we can calculate for the dielectric medium for which the permeability is same. So, if I take pure dielectrics, dielectric media, then for these media mu 1 is equal to mu 2 is equal to, let us say, mu 0, and then the Snell's law essentially would be square root of epsilon 1 sine of theta I is equal to square root of epsilon 2 sine of theta t, and epsilon 1 we can write down as epsilon 0 times epsilon r1 relative permittivity. So, square root of epsilon 1 is equal to square root of epsilon 0 into epsilon r1, that is equal to square root of epsilon 0, and square root of epsilon r1 as we have seen is nothing but the refractive index of the medium. So, we can call that as n1, where n1 is refractive index of medium 1 Similarly, we can have epsilon square root epsilon 2 is equal to square root epsilon 0 epsilon r2, that is equal to square root of epsilon 0 into n2, where n2 is refractive index of medium 2. So, if I substitute now this in your generalized Snell's law, this square root epsilon 0 will cancel on both sides. So, I will get finally a relation which will be n1 sine of theta I, that is equal to n2 sine of theta t, or the way we write the Snell's law, sine of theta t will be equal to n1 upon n2 into sine of theta I. This is the law which you are familiar with, because we have already studied this law in optics in our high school physics, that if a light ray is incident at an angle theta I, and if the refractive indices of the two media are given by n1 and n2, then the transmitted or the refracted angle, which is theta t, that will be related by this. So, this was a special case of the Snell's law for dielectrics. So, this will be a special case of the Snell's law. So, in fact, when we studied this law in high school physics, they appeared almost like these laws came from nowhere. However, these laws essentially come from the wave nature of the light, and since light is a transverse electromagnetic wave, when it is incident on a dielectric interface, it has to satisfy certain phase conditions, and from the phase condition we establish these laws of reflection and refraction. So, let me summarize what we did. We started with a wave propagation in some arbitrary direction. Then we said if the wave is propagating in some arbitrary direction, it creates a phase gradient on the media interface. This phase gradient is same for the waves which are induced on the two sides of the media, which we call as a transmitted wave and reflected wave. And then we found that changing the direction of the wave and creating the phase gradient are essentially equivalent. So, if I change the direction of the wave, I get a phase gradient. Conversely, if I create a phase gradient, I get a change in the direction of the wave. So, what we find here is that the field which are induced, they have the same phase gradient which are created on the interface, and from there essentially we can find out the directions in which the waves will be traveling. So, we found this relation that the direction of the wave propagation is, we can find out from here, that is the angle of the wave which it makes with the normal will be minus times the phase gradient divided by the phase constant in that medium. Sine inverse of that gives me the angle with which finally the wave will be traveling in that medium. So, using this nature essentially we establish the laws of reflection and also the Snell's law, which gave the relationship between the incident and the transmitted wave. Once we understand this, then the analysis of the wave propagation across the dielectric media is quite straightforward. The idea here now is that you write down the phase function on both the media for all the 3 waves, match the boundary conditions at the interface, and then find out the amplitude of the field, electric and magnetic fields in the 2 media for these 2 waves with respect to the incident wave. So, let us say if I have an incident wave which is having an amplitude which is Fi, or for electric field which is Ei, or magnetic field Hi, then we want to find out what is the relative amplitudes of the electric and magnetic fields for the reflected wave and for the transmitted wave. So, let us say we now have a wave and which will be having electric and magnetic fields. So, now the problem essentially we want to investigate is, there is a wave which is incident on this, we know this is going to get reflected at the same angle, part of the thing, this angle is now theta I. So, this angle also is theta I, because theta r is equal to theta I, and this angle is theta t. So, this is the incident wave. So, let us say this one had a electric field which is given by Ei. Say I take electric field for this is given by Er, and I take here the electric field which is given by Et. So, we have a magnitude for the electric field. These are not directions of the electric field, these are the wave vectors. The electric field will be oriented in some direction which will be perpendicular to the wave vector, that we will see in a minute. But if we have now the amplitude of these 3 fields which are given by Ei, Er and Et, we want to find out what is the relation between these 2. So, what is the ratio of this and this, and that quantity we call as a transmission coefficient for this interface, and the ratio of Er and Ei we call as the reflection coefficient for this interface. So, we again have the quantities which are we are familiar with in some sense, because reflection coefficient at least we have seen in case of transmission line, that is whenever we are having an impedance mismatch, the part of the energy is reflected. We are having same situation here, that when the wave travels in this medium, it suddenly sees now a change in the impedance, the intrinsic impedance, and because of that impedance discontinuity, the part of the energy is reflected, and we want to know what is the reflection coefficient, which is the ratio of Er and Ei. So, for this there are 2 quantities of interest. One is the reflection coefficient, and let us denote that as gamma, and that is equal to your Er divided by Ei, and then we can define what is called transmission coefficient, generally it is denoted by tau, and that is equal to Et divided by Ei. Now, since we are defining this coefficient for the electric field, we can specifically call them as the electric field reflection coefficient and electric field transmission coefficient. The similar quantities we can define for magnetic field also, but as we know, since the electric and magnetic fields are related to each other by the intrinsic impedance of the medium, if we know this quantity is electric field in the 3 media, then we can find out appropriately the magnetic fields also. So, the important thing to note here is that the wave which was incident on this was a transverse electromagnetic wave. So, the ratio of E and H was equal to intrinsic impedance in this medium. The ratio of the electric and magnetic field for this wave also is intrinsic impedance of this medium, because this is again a transverse electromagnetic wave, and this wave again is a transverse electromagnetic wave. So, the ratio for the electric and magnetic field for this medium also is intrinsic impedance. So, if I say the intrinsic impedance for this medium, impedance for this medium is, let us say, eta 1, and intrinsic impedance for this medium is eta 2. We know for this medium your EI by HI is equal to eta 1, also ER by HR is equal to eta 1, and ET by HT is equal to eta 2. So, using these relations and the boundary conditions at the interface, now we will investigate what will be the reflection and the transmission coefficient. Keep in mind now that since we are now dealing with the vector quantities, the electric and magnetic field will in general make an arbitrary angle with respect to this plane. So, you may have electric field which might be oriented at some angle like this. So, normally what we do, we decompose the problem into taking the component of the electric field in the direction perpendicular to the plane and a direction which is in the plane. So, essentially what we do, any electric field we decompose into two cases, or any general case we decompose into two, what we call as the parallel polarization, where electric field lies in the plane of incidence, and a perpendicular polarization where electric field lies perpendicular to the plane of incidence. So, we have to find out these quantities for these two cases, for parallel polarization and perpendicular polarization, and once we get that, then we can get the total characteristic of a wave which is polarized at an arbitrary angle with respect to this plane of incidence. So, in the next lecture, essentially we will take these two cases specifically, the parallel and perpendicular polarization, and then investigate their reflection and transmission properties across a dielectric media.